Polar differentiation. Objectives. By the end of this lesson, you should be able to find the slope of the tangent line to polar equations and find points of horizontal and vertical tangency. Alright, we want to suppose we're asked to find the slope of the tangent line to a polar curve that is a function of theta. So when we think slope of the tangent line, we should think derivative. And when we think derivative, we should think dy dx. So that's where this formula stems from. And it looks really long and complicated, but this is just really to show where the formula is coming from, so that we don't necessarily have to memorize it, we can derive it. So slope of the tangent line is dy dx, and dy dx can be thought of as dy d theta over dx d theta. So that's true because if I have dy d theta over dx d theta, it's like multiplying by the reciprocal. And so the d thetas cancel out and we get back to dy dx. So that's how we go from this step to this step. And we can think about this as taking the derivative of y with respect to theta. So in other words, we can kind of pull the y outside, and we're taking the derivative with respect to theta of y, and on the bottom, the derivative with respect to theta of x. But when we talk about polar curves, y is thought of as r sine theta. So now we're taking d theta of r sine theta. And now the variables match, or at least so far the thetas match, and we still have this r involved. And on the bottom, x is r cosine theta. So now we're taking the derivative with respect to theta of this product. So r is one function, r is f of theta, and cosine theta is another function, so this requires a product rule. Both the top and the bottom require a product rule. So the product rule is first times the derivative of the second plus the second function times the derivative of the first. So that is what you see here expanded out. What we need to remember is that r is actually f of theta. So r is a function of theta. So this is actually going to be some function times cosine theta plus the derivative of the function times sine theta. And then the bottom, same thing. R is a function of theta, and r prime is the derivative of the function of theta that r is defined to be. So it kind of looks like a long, daunting formula, but really it's applying the product rule, and it's using the relationship between polar and rectangular coordinates, and just remembering the slope of the tangent line is always dy dx. Alright, the formula is going to make a lot more sense when we do an example. So find dy dx given r equals sine theta, then find the slope of the polar curve at theta equals pi over 2. So find dy dx, we're still being asked to find dy dx even though our polar function has no y's or x's in it. So what we have to do automatically is think about this as doing d theta of y and then d theta of x. So in other words, y, so we're doing d theta, my y value is r sine theta, and on the bottom my x value is r cosine theta. But r isn't a variable, r is the function sine theta. So now let's substitute that in. So we're plugging that in here and here. So we're about to have d theta of sine theta, sine theta. So sine theta, the first one is r, and the second one is this one here. And then in the denominator, I am also doing d theta of r. So r, again, is sine theta, and that comes from what we were given. And then the bottom is times cosine theta. So this corresponds to r, the cosine theta corresponds to the fact that x is r cosine theta. So now at this step, I'm asked to take the derivative with respect to theta of sine theta times sine theta. So we can think about this as a product rule. So the first function is sine. So the first times the derivative of the derivative of sine is cosine, plus the second function, sine, times the derivative of the first, which is cosine. And then all over, I have to do the product rule in the denominator. So the first function, sine theta, the derivative of cosine is negative sine theta plus the second function, cosine theta, times the derivative of the first, which is cosine theta. So this here is dy dx, as long and ugly as it is. We can do a little combining. On the top, I have 2 sine theta cosine theta. And in the denominator, I'll write this as cosine squared theta minus sine squared theta. So this is pretty much as simplified as it can get. If I really wanted to, I could apply the double angle identity here and combine this numerator, but that's unnecessary. This here is dy dx. And then we were asked to find the slope of the polar curve at theta equals pi over 2. So in other words, find dy dx at theta equals pi over 2. So now our dy dx is in terms of theta, so we're just substituting that value in. So 2 sine pi over 2 cosine pi over 2 over cosine pi over 2 as a quantity squared minus sine of pi over 2 as a quantity squared. So here the numerator ends up being 0 because cosine of pi over 2 is 0. But we do have to double check to make sure the bottom is not 0, otherwise we have a derivative that is undefined, so it wouldn't exist. But cosine of pi over 2 is 0, but we're subtracting sine of pi over 2, which is 1. So this is 0 over negative 1, which is just 0. So the slope of the polar curve at theta equals pi over 2 is 0. And then this is my dy dx. And the next example, find the points of horizontal and vertical tangency to the graph of r equals 2 minus 2 cosine theta. So when we think about horizontal and vertical tangent lines are horizontal where the derivative is 0. So we're looking for places where dy dx equals 0, but vertical tangents happen where the derivative is undefined. So those are the two things that we're looking for. So that means we're going to need dy dx, and I don't have a function in terms of y or x. I have this polar equation, 2 minus 2 cosine theta. So that means we're going to have to apply the formula for the derivative involving my polar equation. So let's go ahead and start writing all that out. So my dy dx equals the derivative with respect to theta of y. So y being, I will write it out. So d theta of y, so d theta of r sine theta. And then the denominator is d theta of x. So that's d theta of r cosine theta. And so now here's where we actually plug in the function that applies to us. So my r is actually this function over here, 2 minus 2 cosine theta. So this one's going to be uglier than the last one because we are doing d theta of my r, so that's 2 minus 2 cosine theta. And I'm also going to write that on the bottom. So 2 minus 2 cosine theta, that's my r value. And on the top, r is being multiplied by sine theta, but on the bottom, r is being multiplied by cosine theta. And we're doing d theta. So this here is the first main step to realize that's how we're going to introduce the concept of theta, even though it's dy dx. And then from here to here is how we're going to introduce this idea of r and theta in replacement of y and x. And once we get to this step, it's a product rule. So there's really no need in memorizing that formula that was at the very end. That's the product rule being applied to r sine theta and r cosine theta. So we're going to do the first function, 2 minus 2 cosine theta times the derivative of the second. Derivative of sine is cosine. Plus the second function, sine theta, times the derivative of the first. So the derivative here, the derivative of 2 is 0, and then the derivative of my cosine function is going to be negative sine, but this negative here will cancel, so we get 2 sine theta. And then all over, this is ugly, the product rule again, so the first times the derivative of the second, so derivative of cosine is negative sine, plus the second function, cosine theta. and then times the derivative of the first again, which is still the same. It's 2 sine theta. Alright, so that is dy dx, but what we're going to need to do is figure out where the top equals 0, because where this top equals 0, that's where dy dx equals 0. So these are the horizontal places, the horizontal tangent line locations, and then when the bottom equals 0, those are the vertical tangent line locations, because then my derivative is undefined. So let's go ahead and make a little bit of space here. So ultimately, I'm setting this numerator equal to 0. So let's see how this is going to work. So let's go ahead and start to distribute and see what we can do. So we have 2 times cosine theta. So 2 cosine theta minus 2 cosine squared theta. So up here, I'm distributing this cosine to both parts. And then plus 2 sine squared theta. So this is the numerator. And so we want to set this equal to 0. And I'm going to tell you right now, you're not going to like all the work we need to do to get the answer, because we need to use a lot of trig manipulation and Pythagorean identities. So right now I have a cosine theta, a cosine squared theta, and a sine squared theta. If these are both pluses, I would love to use the Pythagorean identity that allows this to become a 1, but because 1 is negative, I can't do that. So here's what I am going to do. I'm going to rewrite the sine squared function to be in terms of cosine squared. So sine squared theta is 1 minus cosine squared theta equals 0. So now everything's in terms of cosine. So 2 cosine theta minus 2 cosine squared theta plus 2 minus 2 cosine squared theta equals 0. Combining like terms here, I'm going to have negative 4 cosine squared theta plus 2 cosine theta plus 2 equals 0. And I'm going to go ahead and divide everything by a negative 2. Or I can think about multiplying both sides by negative a half, so that I can get rid of both the negative leading coefficient and everything is divisible by 2, so it'll make my numbers a little nicer. So I'm going to have 2 cosine squared theta minus cosine theta, and then minus 1 equals 0. So distributing in that negative 1/2 to everything. And so now on the left, this factors. So this is a pre-cal thing where this is in what's called quadratic form. So it factors to 2 cosine theta, and then we're going to have a cosine theta. So imagine this kind of replicates 2x squared minus x minus 1, but in replacement of x, we're going to put a cosine there. So now we're going to need our 1's to match up, and we're going to need to have a negative x, or really negative cosine, because that is what is in place of x right now. So that means we're going to need the negative to correspond to the 2 cosine on the outside, and the plus to go with the cosine on the inside. So if we were to distribute this, we would get 2 cosine squared minus 2 cosine plus 1 cosine. So we'd get a minus cosine and then a minus 1. So now that these are being multiplied and equal 0, I set each part equal to 0. So 2 cosine theta plus 1 equals 0, and then cosine theta minus 1 equals 0. So now I get cosine theta equals negative 1/2. I'm subtracting the 1 and dividing by 2. So when does cosine theta equal negative a half on the unit circle? So the reference angles we're thinking about are pi over 3, the multiples of pi over 3 in the appropriate quadrants. So where is cosine negative? Cosine is negative in quadrants 2 and 3, and we need a reference angle. So we're looking at quadrant 2 and quadrant 3. We're looking for reference angles that are pi over 3. So here's pi over 3, here's pi over 3. So the major angle in standard position that are my solutions are 2 pi over 3, and going all the way around, that is 4 pi over 3. So those are two solutions. And then solving this equation here, we have cosine theta equals 1. So when is the x value equal to positive 1? That happens only at 0. So this coordinate point is 1, 0. So the x value is 1 at an angle of 0 degrees or 0 radians. So these are my theta values that make the numerator equals 0, which means these are the places of horizontal tangency, but these themselves are not coordinate points. So we have to remember that r equals 2 minus 2 cosine theta. Coordinate points in polar have to be in r comma theta. So we have all of the angles. Now we need to plug them in to get my r. So I'm pretty sure by now you're over this problem, and I'm sorry about that. It is a lot of trig, and I kind of brushed over a lot of the trig, assuming that you know a lot of it. So if you need to brush up on it, then please come and see me. But we are just going to keep on plowing through with this. So r of 0, so cosine of 0 is 1, 2 minus 2 is 0. So that means one place of horizontal tangency is 0, 0. R of 2 pi over 3, so 2 minus 2 cosine of 2 pi over 3. So we just said cosine of 2 pi over 3 is going to give us negative 1/2. We kind of already did the hard part for that. So this is going to be 2 minus 2 times negative 1/2. So it becomes a plus. And this is 1, so this is going to give us 3. So that means another coordinate point. So this was one answer. And then my r value is 3, and my angle was 2 pi over 3. So that's going to be another one. So my directed distance goes first. That's 3. And the angle is 2 pi over 3. And we would also plug 4 pi over 3 in, but hopefully you can see it would give us the exact same answer here. So 4 pi over 3 is going to be the third place of horizontal tangency. And if you can believe it, we're not done, because that's only horizontal tangent lines. We still have to find vertical tangent lines. So that is setting this denominator equal to 0. Alright, so now the last part, we set the denominator equal to 0, and I moved it because we're going to need some space here too. We're going to need to distribute this negative sine theta into both. So we're going to need negative 2 sine theta, and then we're going to have plus 2 cosine theta sine theta, plus 2 cosine theta sine theta is going to need to equal 0. So now, 0. So these two are like terms, so it's going to become 4 cosine theta sine theta minus 2 sine theta equals 0. And so this is a little bit nicer to factor. I can take a 2 sine theta out of both. So 2 sine theta will leave us with 2 cosine theta minus 1 equals 0. So now we're setting 2 sine theta equal to 0 and 2 cosine theta minus 1 equal to 0. So I'm setting each of these parts equal to 0 using the zero product property. Divide both sides by 2, I get sine theta equals 0. Here, let's move the 1 to the other side and divide by 2, so we're solving when does cosine equal positive 1/2. So this is going to happen still at reference angles of pi over 3, but now we're in quadrants 1 and 4 where cosine's positive. So my two solutions are pi over 3 and 5 pi over 3. And when is sine, the y value 0? That happens at 0 and pi. So that's when my y value is 0 at these two angles. Now our job is to find the coordinate points of vertical tangency, so we need to substitute 0 and pi, pi over 3 and 5 pi over 3 into my r function, 2 minus 2 cosine theta. So let's start with 0. If we have r of 0, we have 2 minus 2 cosine of 0. Cosine of 0 is 1, so we get out 0. And this should give us pause for a second, because now we're saying that 0, 0 is a place of vertical tangency. And we said earlier that it's a value that made the top 0, and we kind of jumped the gun a little, because we said it was a place of horizontal tangency, but the second we find out that it also makes the bottom 0, then we have a bit of a problem. If dy dx is 0 over 0, then the derivative does not exist at this point. So there's no horizontal or vertical tangent line. The derivative does not exist at 0, 0. So it's neither a place of vertical nor horizontal tangency. So we will cross it off the list from earlier as a horizontal tangent line location. So let's continue on by seeing what the coordinate point is at pi. So r of pi is 2 minus 2 cosine pi. Well, cosine of pi is -1, so 2 minus 2 times -1 gives me 4. So my coordinate point in polar is 4 pi, so that is a place of vertical tangency. And then we'll also plug in pi over 3, so 2 minus 2 cosine pi over 3. So we already know cosine pi over 3 is 1/2. That's how we arrived at that value. So 2 minus 2 times 1/2, 2 minus 1 gives me 1. And if we substitute 5 pi over 3, we will also get out 1. So we have 1 pi over 3 and 1 5 pi over 3 as a place of vertical tangency. So we have 3 places of vertical tangency. And then from our previous work, we have horizontal tangent lines occurring at 3 4 pi over 3 and 3 2 pi over 3, and we are going back and eliminating 0 0 as a point of horizontal tangency because the derivative does not exist at 0 0. So we did all of this work by hand to get the appropriate angles and written in terms of radians. What we're going to do now is we're going to graph the original function and see if our answers correspond to the graph, see if it makes sense. So let's go ahead and graph 2 minus 2 cosine theta. And we'll delete everything else here. So the graph that we see should have, let's see. So let's go ahead and adjust the window a little bit. I want to be a little bit further to the left just to make sure I have the whole graph pictured. There we go. All right, so according to our information, we should have 2 places of horizontal tangency. So let's go ahead and move that over. So my places of horizontal tangency should be happening at 4 pi over 3 and 2 pi over 3. So let's see. We have what looks like a horizontal tangent line right here and about right here. At 0 0, we said the derivative does not exist. So hopefully you can see right there that there's a sharp turn. So we have a derivative that doesn't exist. So we have 2 places of horizontal tangency, and those are occurring at angles. So let's remind ourselves too, 2 pi over 3 and 4 pi over 3 are in quadrants, 2 and 3. So that looks like that makes sense so far. And then the other information that we had vertical tangent lines occurring at 3 places. So we'll notice that there are 2 vertical tangent lines right here and right here in quadrants 1 and 4. Those correspond to pi over 3 and 5 pi over 3. And we have another vertical tangent line occurring at pi. So pi is over here 180 degrees, and how many units away is that point? 1, 2, 3, 4 units toward pi. So that's confirms that we've done everything correctly, that we have 3 vertical tangent lines, 2 horizontal tangent lines, and 1 place where the derivative does not exist. I have a sharp turn there.